So we are looking at the definition of WSP of omega, S in R, and 1 less than equal to P less than infinity. So if S equals minus M, M in Z, M greater than 0, then we defined it as the W minus MP 0 omega star equals W minus M P dash omega. So this is how we define. So in this case there is some, I want to correct something which I wrote last time. So I wrote the following: since WMP 0 omega contains derivatives of LP dash omega functions, we denote it by W minus M P dash omega. Okay, so maybe not 1P omega minus 1P dash. Okay, so there's you might have noticed the mistake. So this is, it should be the dual in this place, and that is please correct that mistake which we have. So we said this. Then in case of P equals 2 and omega equals Rn, then we define that Hs of Rn, where is equal to set of all u in L2 of Rn such that 1 plus mod xi square to the s by 2 u cap xi belongs to L2 of Rn when s is positive, and H minus s of Rn is set of all u in s dash of Rn tempered distributions such that again 1 plus mod xi square to the minus s by 2 u cap xi is in L2 of R. Okay, so this is both of them for s greater or equal to 0, and this is how we define, and then we showed that in fact when s equals 1 this is indeed the case. So now let us by definition, if u is in L2 of omega and du by dxi are in L2 of omega, 1 less than equal to I less than equal to n, then by definition this means u is in W1p of omega. Similarly, if u is in WMP of omega, m positive integer, and du by dxi are also in WMP of omega, again by definition this implies that u is in Wm plus 1p of omega. Okay, so this is just comes by definition. So now we want to extend this to the case of negative indices also, and so we have a very nice lemma. So this is a theorem, and it goes by the name sometimes of lemma of Lions. Okay, so omega equals Rn, Rn plus, or a bounded open set of class C1 in Rn. If u belongs to h minus 1 of omega and du by dxi is also in h minus 1 of omega for all 1 less than equal to I less than equal to n, then u belongs to L2 of omega. So proof, we will do it in the case omega equals Rn, where it's very easy. Okay, so if u du by dxi are all in L2 of Rn, then you have that 1 less than equal to I h minus 1 less than or equal to n, then 1 plus mod xi square to the minus half of u cap xi and 1 plus mod xi square to the minus half of xi u cap xi, because I am taking the Fourier transform of du by dxi is xi du by dxi with a 2 pi I coming in, but that's just a constant. So all these belong to L2 of Rn, and this means that integral 1 plus mod xi square to the minus 1 into 1, which comes from this term, plus mod xi square sigma I equals 1 to n, which comes from this term, and so Rn mod u cap xi square d xi is finite. But then these two cancel off, and therefore this tells you that u cap belongs to L2 of Rn, and therefore it implies that u also belongs to L2 of Rn. Now the proof for the other cases, namely for Rn plus, is bit involved and complicated, and then once you have that, then by the usual patching up with coordinate charts, mapping with the cube q on the boundary, and then using partition of unity, the usual tricks, we can prove it in the case of any omega of class C1, because class C1 means there's a whole machinery available, namely each point on the boundary as a neighborhood with some special properties, etc. So that can be done. So for a full proof, so see the book of Duo and Lyons, where you can have a proof of this. It's not very easy. Okay, several generalizations of this result are available, and one of the most comprehensive results is due to Ambrouche and Giraud, which says that if omega is in R3, so in particular we take omega in R3 and m is any integer in Z, positive or negative, and if V belongs to d prime of omega such that dV by dxi belongs to hm of omega for all 1 less than or equal to I less than or equal to n, then this implies that V belongs to h m plus 1 of omega. So V is just a distribution in this case. Okay, so in fact we have done one exercise long ago in the where we said that if V is in a distribution such that dV by dx is in L2, then V is in H1. Okay, so we have seen such things here. Okay, so now we will use this Lyons' lemma in a very nice way to prove a very important inequality, which is fundamental in the theory of elasticity, which we will see in the next chapter. Okay, so for that we need some notation. So notation: omega contained in R3, bounded open set, bounded connected open set, class C1. V equals h1 of omega power 3. So each component is in h1 of omega, and you have the product norm. So if V equals V1, V2, V3 in V, so then we define for 1 less than or equal to Ij less than or equal to 3, epsilon Ij of V is, so this is the definition, 1/2 of dvi by dxj plus dvj by dxi. So these are called, for instance, in elasticity theory, this is called the strain tensor. Okay, it's a symmetric thing, ij is same as ji, so this is called a symmetric thing. So norm v is the usual product norm which is got from h1 of omega. Okay, so theorem, this is called Korn's inequality. Let omega contained in R3 bounded domain which means connected open set of class C1. There exists a C greater than 0 depending only on omega such that for every v in V we have integral on omega of sigma ij equals 1 to 3 mod epsilon ijv square dx plus integral on omega sigma I equals 1 to 3 mod vi square dx is greater or equal to c times norm v square. Norm v is nothing but sigma norm vi square 1 omega. This is the usual product norm which we have. Okay, so in other words we are saying that, okay, we will come to that. Okay, so proof. Define E to be the set of all V in L2 omega cubed such that epsilon ij of V belongs to L2 of omega for all 1 less than equal to ij less than equal to 3. So in particular V is contained in E, because if V is in H1 all the first derivatives are in L2 and therefore epsilon ij of V is also in L2. Okay, so automatically we have V is contained in E. Then you equip norm on E is given by V, norm V on E equals integral on omega epsilon ij V square dx, now that they are all finite, plus sigma I equals 1 to 3 mod vi square dx, and then the whole thing power half. So then E is a Hilbert space with this norm. I leave you to check this. So this is some simple checking which you have to do. So you just have to show, well, it's a norm, it comes from an inner product, is obvious because you have all L2 terms here, and then all you have to do is to check it is complete. Okay, so if you take a Cauchy sequence, already it will be Cauchy in L2, so you will have a convergent subsequence. Then you have to show that this will also have epsilon ij of V will also converge to some Vij. Now you must show that the limit is precisely epsilon ij of the limit of the V's. Okay, so that is the standard checking term. Now easy calculation gives the following: d2vi by dx j dxk equal to d by dxj of epsilon ik of V plus d by dxk of epsilon ij of V minus d by dxi of epsilon jk of V. Okay, so this is just algebra. You just have to write out, expand this, then take d by dx, whatever you have take, the many things will get cancelled and you will end up with just d2vi by dxi dxi. This is a very straightforward calculation. So then if v belongs to E, then what can you say? Each of these is in L2, you are taking the first derivatives, therefore d2vi by dxj dxk, they all belong to h minus 1 of omega. But dvi by dxj is also in h minus 1 omega for all ij, because vi is in L2, take the first derivatives. Therefore, by Lyon's lemma, we have that dvi by dxj belongs to L2 of omega for every pair ij. So the vi's are all in L2 and the first derivatives are all in L2, so this means that E is contained in V. And the converse we already showed, so E is equal to V. So you have that the two spaces are, as vector spaces, they are the same. Now we know that norm V in E is clearly less than or equal to C times norm V in V by the definition. What is norm V in E? It is the L2 norm of the Vi's and epsilon ij of V. So they are all first derivatives. So if you take the square, take the L2 norm, etc., that will be less than some constant times the norms of the first derivatives, and therefore you will get that this is nothing but less than or equal to constant times this. That means the identity map from V to E is continuous, which means by the open mapping theorem, 1 on 2 continuous implies identity map is an isomorphism, therefore norms are equivalent, and that is precisely, that is Korn's inequality. Because what is the Korn's inequality? It's precisely saying norm V is less than C times the other norm. Okay, so that is exactly the Korn's inequality. Okay, so this is a very nice application of the open mapping theorem, and it is nice, it's an important inequality in the theory of PDEs. Okay, so now we conclude with what we call the trace spaces. So we are going to deal with P equals 2, though we can deal with other things. So we want to define Hs of gamma, where gamma is nothing but d of omega. Okay. So omega in Rn, n greater than or equal to 2. Okay, open set. So assume omega of class C infinity. So this much is not necessary, but we don't want to fuss around, so we'll assume maximum smoothness so that we don't have to make any qualifications anywhere. But of course you can reduce the necessary smoothness certainly. And locally on the same side of its boundary. So when you move along the boundary, the domain is always on one side of it, depending whether you go clockwise or anti-clockwise. So you have domains like this. So if you go like this in the anti-clockwise direction, the domain will always be on the left of it. So what we are not allowing is that a domain like this. Suppose I have a domain like this, and this is also taken away. Now this domain, so you have a domain on both sides of this boundary, and therefore this is not allowed. Okay, such domains we. So now gamma equals d omega is compact. Okay, omega class of C and bounded. So you can cover by finite number, omega of class C infinity, and it's same side of the boundary. Okay, and since you say gamma is when you say class C infinity, we mean bounded boundary, and therefore gamma will be compact. So we can cover by a finite number of neighborhoods uj, j equals 1 to k, and there exists C infinity bijections Tj from Q to Uj. If you recall, so you had Q here, and then you had the boundary, so every neighborhood you have U, so Q plus will be mapped to U intersection omega, and then Q0 will be mapped to d omega intersection U, okay, and all these Tj and Tj inverse are these are Tj inverse are all C infinity maps. So associated partition of unity psi j equals 1 to k. So we are only covering the boundary now. So we have finite number of sets for the boundary. So that's an open collection of open sets. Union is open. So you take a partition of unity corresponding to that. Okay. So support psi j contained in uj, 1 less than equal to j less than equal to k, 0 less than equal to psi j less than equal to 1, and also sigma psi j equals 1 to k identically 1 on gamma. Now gamma is a smooth n-1 dimensional manifold, implies there exists a natural measure on gamma induced by the Lebesgue measure on Rn. You can do this in many ways. You can use the induced Lebesgue measure. You can also call the n-1 dimensional Hausdorff measure. Minkowski contained the various ways of defining the measure. However, since the domain is smooth, all these things will agree with each other, and therefore you have some natural measure, n-1 dimensional surface measure, natural, so n-1 dimensional surface measure on gamma induced by a Lebesgue measure in Rn. Therefore, we can define, easy to define, Lp of gamma for p greater than or equal to 1. Okay. So now let U belong to L2 of gamma. So then you can write U equals sigma j equals 1 to k psi j u. Okay. Now psi j u supported in uj. Now you consider Vj of y dash 0. So y dash is in Rn minus 1, okay, equals psi j u of Tj y dash 0. So what are you doing? You are taking a point on the axis in Q. From there you are going to uj to the boundary here, and then you are taking the value of u psi j u, which is supported in this set, and then so for all y dash 0 in q0. Now support of Vj is contained in q0, so extend to Rn minus 1 by 0 outside q0. Now u going to Vj 1 less than equal to j less than equal to k, take maps L2 of gamma into L2 of Rn minus 1. Because you have taken the image using some C infinity maps, this is in L2, then and then therefore this will be in L2 Q0, outside you have extended by 0, and therefore they are all in L2 of Rn minus 1. So if S is positive, then you define Hs of gamma equals set of all u in L2 of gamma such that Vj belongs to Hs of Rn minus 1, 1 less than equal to j less than equal to k. Now must check, we won't do this, must check that this definition does not depend on the choice of the covering uj j equals 1 to k of gamma. So whatever cover you take, finally the spaces which you get will always be the same. And if we define H minus S of gamma as Hs of gamma star, the dual space. Okay, so this is how we define Hs spaces on the boundary. You can do it for the other P also. We've done it for P equals 2. There's similar way you can easily do it for other P's as well. Now these are called the trace spaces, which we will use in when studying boundary value problems later on. Okay, so